So I encourage you to stay a little bit longer with us. This is not yet over before we go to a lunch break. This is our last talk. And as was already mentioned today, the quantum technologies need also classical counterparts to make them work. And we have a very exciting speaker today. Dr. Claudius Riek, Managing Director of Zurich Instruments, is joining us today, and he will speak about how to connect quantum world and classical worlds. In his current role, he is responsible for scientific collaborations in Zurich Instruments, exactly in Europe and Germany. It's a great pleasure to have you here. Please, the stage is yours.
I think now it works. Thanks for the introduction. So Vadim made the right point, or made a very important point, yeah? There is no point having quantum information in a quantum system if we cannot access it, if we cannot make it usable. And therefore, very crucial, we have to connect the quantum world to our classical world. And this is precisely the business in which we are in. Yeah? And this is also, I want to talk how established industries can help with this task. I'm part of Zurich Instruments, and Zurich Instruments is part of Rohde and Schwarz. And this is important to understand. Yeah? Zurich Instruments started up 10 years ago from the, as the name says, ETH Zurich. And now we are part of the Rohde and Schwarz company. We are part of the test and measurement part, but there are more things at Rohde and Schwarz. We have the technology systems, we have the network and the cybersecurity part, and as we will see, there are connections to all three of those divisions. So, quantum technologies, what does that actually mean? What does it contain? It contains quantum computing, many things were said about that already, quantum metrology, what includes quantum sensing naturally, and of course quantum communication. And we engage in all of them, but in very, very different ways. In the end, we have three parts which we take as our quantum mission, or mission for quantum. Enable, we are a supporting part for enabling quantum technologies. Engage, being close to the community, and also in the end integrate some solutions. Let's start with the first part, enable. What does that mean? What is a typical example? Typical example is connecting a quantum computer to the real world, so to say. Yeah, here we have a typical impression from the lab. Let's see if this animation works. We need to send signals to the quantum chip, to the actual qubits, as Professor Wunderlich described before, and there is where we need the precision. And yeah, to make it a little bit more clear, we have on one hand side, there are frameworks like Qiskit, etc., so where the actual user sits. Maybe use that, so where the user sits, this all needs to be synthesized in certain control pulses, which are going down. Then here's the superconducting processor, go down to the actual qubit, in this case a manufactured, not a natural qubit, as we just learned where difference is. And then we read it out, and the whole cycle goes also back, where the information, where the result then of the quantum algorithm is processed. And how crucial the part of the control electronics, so the part of connecting the qubit to the real world is, we see from the DiVincenzo criteria. I will not read it, you will all know them. If we look at the first two, yeah, we have, they are for the actual quantum systems, the qubits. We have neutral atoms here, superconducting qubits. We want to have there a scalable system. We want to have a physical system with great decoherence time. So we want to be able to interconnect with the quantum states for quite some time before they decohere. But there is, and there are very many different ways. Yeah, there are neutral atoms, NV centers. I think we heard all of them today already, so I will not go into the details. But what we also learned, on the left-hand side, you have the ones which are interacting with laser light. On the right-hand side, you see the ones which can only rely on electrical signals, so microwave signals in the end. And this is precisely where we need to have technology which is able to precisely initiate a state in a qubit, and also have the ability to quickly measure. And of course, we need to do that all with a universal set of quantum gates. And Professor Wunderlich mentioned the precision required to control qubits. For example, he mentioned the frequency stability in particular. Yeah? The great thing is there are actually many industries which already work on that. There is technology, for example, radar, yeah, which have very similar requirements, so we can build on top of that. And this is where we can also see where you can see some of the parts of the portfolio, because you need the different technologies. So on the left-hand side, you see more from the design all the way to the operation. On the left-hand side, you see typical devices which you've most likely seen in a lab, whatever, oscilloscope, network analyzer, etc. But they are very new requirements for quantum applications. To name one, how to measure the phase noise of adjacent pulses if you have a different pulse signal in between. This is something which is sounds like, okay, you just measure it, but actually it's not so trivial. And this is precisely the point where other industries or enabling technologies can really help. And this is where we see a big impact for us. Then you have, in this case, also on the right-hand side, where it goes into the operation systems, the electronics. You want to have hundreds of channels. Heike Riel mentioned this morning, we want to have 100,000 channels. For superconducting qubits, this means you need to have you need to send an individual signal to each and every single qubit with the precision required and also with the timing. This alone is quite a challenge. And I think we need to work together from different industries, also from different backgrounds, physicists, electrical engineers, and computer engineers, to make this in the end happen. And to show you a little bit where very different capabilities play a crucial role is, let's go through the situation. Okay, if we have a few qubits there, first of all, we want to understand how does this qubit actually behave. So we need to measure it. We need to characterize it. Then we need to come up with a bring-up routine. We need to bring it to the ground state or the excited state, depending what we want to perform. And we need a certain amount of flexibility, because also nowadays, transmons are very, very well established, but even in the part of superconducting qubits, we have more architectures coming up, which require big flexibility from the control electronics, how to interact with those. Then if we have a few more qubits, we can do fascinating things like, for example, implementing a surface code. So error correction, you need to have feedback. You need to have, for quantum error correction, we need to have the capability to do classical decision making in a very, very short amount of time to keep track with our quantum system, which is ongoing at the same time on our QPU. And of course, thinking even further, we also need to bring this to a scalable architecture. And this shows a pretty big rise that with a lot of space for electronics and cabling and actually big QPUs. But there are other concepts. The question is, okay, can you do a tileable control? Can you distribute the actual quantum computer to mitigate the challenges which you have if you want to have, for example, hundreds of thousands of, in this case, superconducting qubits, but also other qubits in a very small, in one computer. And of course, we have on the other hand side questions like HPC connectivity. We have computer engineers who want to actually work on those instruments, so we need to find a way how to connect them to our real world. And yeah, to show also one of the points where this worked very well together is we collaborate very, very tightly with IQM. We have been able to accelerate in the end their success so far by reducing time to market. They don't have to work on the entire chain. They can really focus on what is crucial for their technology, the qubit chips, and how to interact with them. But let's continue. It's not only enabling, it's also engaging. How do you engage? Most simple question, you do projects together. I want to pick a completely different one, quantum radar. Quantum radar is a project where some of my colleagues are working very closely together with colleagues from WMI and also DLR with the clear idea to show how quantum radar can work. There's the goal to have something like 3 dB SNR improvement, and of course the test and measurement part of the industry wants to see, okay, what do we actually need? What do we need to go for the next step? What do we need to support this upcoming industry? How it works, and I think this also shows a little bit the challenges. First of all, you start with entangled photon pair in the end, coming from superconducting fridge. You send it out via antenna. The signal goes out, the idler kind of stays in the radar component. This requires something completely new, quantum memory. Yeah, so the question here, which is addressed, how can we actually store this quantum information to, in the end, again, make the joint measurement and hopefully show how we can achieve a radar which is better than any classical radar would ever allow. But there is more. It's also the Zurich Instruments collaboration projects. Here listed a few. I would like to pick up especially one or two. First one is QSolid, one of the projects in Germany, national projects in Germany, where we are working on scaling a quantum computer. It's about enhanced error correction, also HPC integration of a quantum computer in the end in Jülich. So also here it's the question, hey, can German collaborators do that on premise in Germany with cloud access and whatever you want to wish to show it to people who want to, I think Professor Wunderlich said, play with a quantum computer. There is more, because we see Germany is a very crucial part. We are located in Munich, but there is the European community, and there we are part also of the Open Super Q Plus project, which is going exactly also the route which is paved by others globally. There, the goal is to first achieve produce a 100 and then a 1,000 qubit quantum computer by, again, not only one individual startup doing that, but multiple people contributing with their expertise, bringing, for example, we have Rohde and Schwarz in there, we have, but also VTT in there, big technology lab in Finland, and also Blue Force, which most of you have already seen on one of those big fridges, and always when you need to cool, for example, a superconducting or semiconducting qubit chip. And with that, we come to our third mission. Because we had the enabling, which is kind of our main part. Then we have the engagement. And only if you do the first part, 2 parts in a good way, then you can actually also start integrating quantum technologies. Because also here, we want to make quantum technology accessible and allow industries and also end users to benefit from advantages of quantum technology. And one of the first part is we have a Rohde and Schwarz encryptor, and we want to be sure that this is ready for quantum key distribution, because this is not the case for any encryptor for cybersecurity. You have to ensure that you already at the very beginning start in the design on the classical electronic, that you don't destroy the quantum advantage which you have to get first of all by generating your quantum key in a very difficult way to get and to not to destroy this advantage further down the line. Therefore, we also participate in multiple projects. We want to stay close to this new and emerging field. And with that, I would like to conclude. Our mission is enable, engage, and also integrate quantum technologies. And with that, let's push quantum forward together. Thank you.
Thank you very much, Claudius. I would like to open for discussion, for questions. If there are some questions here in the audience right away, please. Here is one here. You have to speak without microphone, I'm afraid.
Thank you, first of all, for a very nice talk. You mentioned your collaboration with IQM. So as we all know, they're doing superconducting quantum computers. So they need strong cooling. Others don't, but then therefore there are different problems. So from your point of view, how is your view on the race between the different technologies when it comes to the challenges on the enabling technologies? For an enabling technology company, what's the most profitable? Okay. So the question is, what in terms of the enabling technologies, where do we see the biggest challenges for the different qubit architectures, and maybe where it's most profitable? I mean, of course, in the end, it's a trade-off. Some need more cooling, so this means we have to solve the question: how can we cool 100,000 qubits to 10 millikelvin or millikelvin regime? On the other hand side, you might need a super big or fairly big laser system, which might cause some other challenges. So depending, of course, the architecture in the end provides kind of the challenge for the enabling technologies. And it goes more or less all over the place. One question I think we should all ask ourselves, also making one of those platforms kind of market ready, if I may go in this direction. What is the other technology we can potentially borrow from? Is there something maybe in classical computing, maybe in MRI? So there's a lot of technology in different parts. So, and I think we should also ask ourselves the question, where can we have the biggest synergies? So I think there's not a single answer to it, but it's really where are the synergies and what can we combine in a very clever way to the new concept together.
No question?
Yeah, first of all, thank you for this interesting talk. Lately, especially in the past few months, there have been new error correction protocols popping up all over the place, where each of them requires more complicated real-time computation to perform the actual correction. How do you plan to integrate these computations?
Very good point. So one of our we integrate as a part in our architecture. In the end, we have distributed FPGAs in the end on the different readout modules. Becomes a little bit more technical now, but there is one big there's one big in the end FPGA, but one big controller in the center of such a bigger system. And having said FPGA, then it's of course the next question: how flexible is that? FPGA you can program in different ways. So we don't foresee at the moment a fixed protocol kind of pushed in an ASIC, and then this is the only thing which can do. But we still see the enabling technologies, the electronics in this case, needs to still have the flexibility to cater to those different steps. And I think it was also in the discussion, in panel discussion before, there was the point of co-development. It's not only co-development of hardware and software together, it's also co-development of the quantum hardware together with, in this case, for example, the readout and the control electronics to enable and those additional steps needed to become, in the end, a logical qubit, which is the goal of all those error corrections.
All right, thank you.
Continue there.
Thank you so much for very nice talk. My question was regarding quantum system solution, one instrument that you showed. Actually, we are using a lock-in amplifier from Zurich instrument, but then you showed me that this picture of superconducting quantum computer from IBM and some of your machines that can integrate with it. So I was curious about it. What was it exactly, and what it do? This electronic machine, like quantum system solution and some sort, like what it exactly do and how can it help in computing, like?
Happy to answer. We can happy to discuss also this in more detail. So for the bigger audience, what the instrument does is it synthesizes the control pulses, which you need to send to the qubit to initialize it, and then to realize the different the quantum gates. Yeah. And it, at the same time, also needs the ability to read out. And it actually works very similar like a lock-in amplifier. Happy to discuss more. It is optimized, or engineered to foster the signal with highest signal-to-noise ratio from the qubits to ensure that we achieve high fidelity. Hope this answered and was also okay for the rest of the audience.
Thank you very much. I would say we close now this slot, and you're welcome to chat with Claudius outside. Thank you very much again.